topic of the talk is diffusion in anamorphic green lens, and this is a little bit what we have done in my research work. Actually, I have completed my PhD work in 2018 under the supervision of Professor Amitabu Basurai, the fourth order of the author of this paper, and Dr. Nisha Shubhishra. They are actually working on applied optics and photonics department in the Calcutta University. And Dr. Nisha Shubhishra was a scientist of Central Glass and Ceramic Research Institute under CSR lab. It is also located in Calcutta. So, and I am now working in Calcutta Alia University as assistant professor. So, sir, my outline of my talk is basically based on these points. One is the background, objective of these works, division, and then the methods we have used, what are the results we have achieved, and conclusions, and some publications on these works. So let's start my first slide. So little bit about the background. As you see, there are two components to lenses are shown over here. One is the conventional lens. As you all know, that its function is to actually make images with the help of converging, diverging, whatever is required. But the thing is that the focusing is being implemented with the help of the curvature in the lens itself. The lens itself is more different. And another one is your flat module, and which is having no curvature in its surface, is the flat one. And due to the inhomogeneity created inside the sample, it can have the ability to the focusing or diverging. So basically, this is the difference in crude rays of the lens having curvature and lens having without any curvature. So gradient index or gradient index optics basically deals with the optical effects which is produced by gradual variations of the refractive index in the material. As I told, the material inside it is not a homogeneous one. The refractive indices of this material will change by some means. We have actually used the ion exchange process to change the refractive index inside the material. Now, these such variations are helpful in making lenses with flat surface, and it has many advantages. One of them you can say that aberrations, lens aberrations, and has the image quality may be enhanced with the help of such lenses. And one of the biggest example advantage is also miniaturization. We can have a multiple elements in a compact way because it does not require the so-called area requirement in case of conventional lens. Now, the control continuous variation in refractive index is the unique features of the green element, and that is if you want to make a different refractive index profile, you have to make such type of arrangement so that you can.
Asraful, please speak very close to your mic. Sometimes your voice is breaking.
Okay, sir, thank you. Okay.
Yeah.
Now, in gradient index optics, we can make different types of lens elements. It may be of axial type, radial type, or spherical type. The thing is that we have to make our sample shape in such a way that it can produce like that. Suppose a planar object can have developed axial. A cylindrical type of object can develop radial, as well as a spherical type of object can develop. So the focus of this presentation is to basically development and characterization of elliptic green lens. It is also known as anamorphic. Its shape is irregular, and it is a kind of elliptic cross sections. So that is why it is called anamorphic. Now we know that in case of normal laser diode, we have some asymmetry. symmetry in terms of its beam shape as well as astigmatism. Astigmatism means the focus of these two. If you see this figure, the two beams, basically vertical beams and the horizontal beam, sagittal plane and the tangential plane are not having the same divergence. And because of this, the shape of output beam is also not circular. It is non-circular, and this non-circular is generated because of the asymmetry inside the waveguide structures of the lasers, and focusing of these two beams are not originated from the same point, but has a certain lateral distance. The lateral separation, you can say, is called the astigmatism inside this laser beam. And because of this, these two rays are being coming out as a two dissimilar angle of divergence. One is called fast axis divergence and is slow axis divergence. So the elliptic beam shapes, once it is emitted, it is sometimes undesirable in many applications because it can give you a irregular or non-uniform optical power, and spot is also not circular. So if there is a requirement of circularity in some applications and uniformity of the beam, you need to make that beam to be circular rather spherical. So as you see, these two beam sizes are there before circulation is this and after the. So there are some means to circularize that, but those means are not sometimes efficient or may take some bulky multi-element systems. As you see, the different approaches can exist. One is your cylindrical lens pair. These two cylindrical lens, you know, the beams, once it is emitted from this cylinder, the two axes will have different animations. And if I have two different divergence, we can make it little bit parallel with the help of double cylindrical lens. And in the similar way, anamorphic prism pair is also very much useful. Anamorphic prism pair can also give the circularity. And another important one is called your filtering effect. That is your special filter can make the signal circular. But in this case, uh, it is basically apodization. Some part of the signal is being lost. And these options are basically used in many applications. And if you see this table, you see that there are methods which can give different types of normalized astigmatism. And in this way, you may be called the cylindrical landscape with the better result. But the main important disadvantage of these are that it is basically multi-element solutions, and multi-element solution makes the thing bulkier, and also handling of the instrument may be little bit complicated. So in our work, our objective is basically twofold, and in first we have actually developed or fabricated this green electric system in a developed glass system, and measurement in refractive index profile and fabrications of the sample it has been done in one way, and it is being reported and published in some paper in this 2012 optic communication. Another objective was to make the concentration profile to be plotted, and so that we can correlate the experimental result we have got here. So based on that, we have uh, prepared this presentation. And first of all, these methods and the sample fabrications, as you know, the glass available in the commercial market may not be suitable for ion exchange experiment, and that's why we have actually made this glasses in this lithium, sodium, aluminum silicate, the silicate glass basically. Some modifier and intermediate oxides are being given to it. And after this, we have made different rod sizes. For example, 30 millimeter long rod size, and the cross section is around 3.5 millimeter is developed. And some sample of this glass has been made. And different indexes have been measured by certain instruments, and also average dispersion values are being calculated. Now the sodium nitrate bath is basically used for exchange purposes. The sodium nitrate bath and the glass itself is being basically carried out for certain hours. For this example, we have taken 370-degree temperature. This temperature is basically near about the 10 plus transition temperature of our system, and 160 hours of exchange duration has been taken. And after that, we have made different slices of 1.5 millimeter thickness, and remaining glass is being made ready for other experimental testing. Now, in this experimental measurement method, we have used a setup where different components have been used, like your laser source, a microscope objective, pinhole, camera, pinholes, and polymetric lens. And this the main component of this is your birefringent lens. And birefringent lens is basically a lens which can create two sources uh, by by means of its property, and we can have two laterally shifted point sources to be created over here, and that two point sources when interfere each other, interference fringe pattern is being developed, and we can have a neutron line circular fringes. And this is the actual setup where this figure where our sample is being placed over here, this part. And initially we have set a base element where there is no exchange is being taken, and two samples of base glasses are being given to the experimental setup. One is showing a uniform circular pattern, and it is also uniform, but it has certain scratch and other noises are there in the sample itself. That has also been shown over here. But these two figures is basically give the fringe changes over two perpendicular directions. This first one is along this major axis, and this one is the when the major axis is vertical and another is major axis is horizontal. And from these two figures, it is obvious that refractive index has been modified in the sample itself, and the modifications are not also same. It is different in two perpendicular direction, and definitely it will be different in between these two directions as well. Now we have been tested these samples by making an imaging setup in the same experimental setup by modifying material, and in this you have still two actually focus tool. One is the sagittal tool and there is the longitudinal tangential focus, you can say. This lens has been basically verified, modifying the setup, whereby the fingering lens and the polarizers are removed, and the green rod sample is placed at the sample position. The collimated beam is focused onto the input end of the rod, and the beam coming out of the other end is then focused by lens. And it is observed that there are two focal planes is being developed. One is for the horizontal and another is the vertical. Because our sample is elliptical and we have developed two refractive indexes profile of different gradient along major axis and minor axis. So when a light beam, collimated light beam is given to it, it will be focused to certain point, but that points will not be actually same. It will be different because of this generation of different optical power in the lens. And this has been again verified by using a beam which is deliberately made more elongated with the help of certain cylindrical lens, and then this beam is being sent one by making our sample horizontal to the major axis and another by making the sample vertical to the major axis. That means when it is horizontal to the major axis, where the refractive index changes is more, it makes the beam more elongated. But when it is given in the cross direction, it is being reduced. That means circularity is being generated by it. So we have qualitatively in this way make our sample to be verified that it has produced a elliptical type of refractive index profile, which can give to focal length, and it can have the ability to make an elliptical beam to the circular one. Now, in the second part, we have actually uh, tried to correlate the results which we have got in experimental findings with the theoretical one. And as you know, that this is the elliptical shape. The coordinate geometry should be followed also the elliptical geometry one. And in case of ion exchange experiment, there is a basically diffusion process involved, and diffusion is guided by fixed law of diffusion. The equation of that diffusion is this, where C is the concentration, it is the diffusivity or diffusion coefficient. So when it is converted to a circular or say uh, rectangular coordinate system with xy coordinate, and we have actually taken 3 by 2 or 6 by say 4 diameter by length size. So the corresponding coordinate transformation will be x and y like this, where x is the focal length and u and v are the two coordinate in the elliptical geometry, and these are interrelated. So here f will be here and 2a to be the major and minor axis. Now, when you put this into our main fixed equation, fixed law, and make the separation of variable technique, we usually get three sets of equation, independent equations. One is this one, another is this one, and third one is this one. And these two equations are uh, specially known equations. These are basically one is called Matthew angular equations, and another is called Matthew radial equations. And here two parameters a and q are being interrelated in this way, that q is equal to lambda square h square by 4. And these two parameters are called separation constant, as well as second one is called characteristic value or eigenvalue. Now, basically in this part we have tried to solve these equations, but in literature we have don't find many equations which is actually useful in diffusion. But in case of this elliptical coordinate system, but some sort of help is being actually taken from a McLachlan book, which is a very old book in 1958, where we have taken some help of uh, these functions, and we have tried to develop the solution. In first case, there is an infinite number of eigenvalues for each of the four annual functions, and the notations used for the eigenfunction is eigenvalues are ARQ and the VRQ. And these ARQ and VRQ are actually relates with the associated angular function C2. So first we have calculated C2V. From the literature, we have found that this angular function is designated by this sort of symbolism, and AR and VR are the coefficients which are generated from the recurrence relations. When we put some boundary conditions on the earlier four equations, we get these four sets of recurrence relations. So with the help of these recurrence relations, we tried to calculate the angular function first. And using this expansion coefficients, we have again generated the radial Matthew function, and which is delivered by C3. Okay, and C3 has two parts as R, dependent on R and N value. And since we are using a geometry which is symmetrical with respect to major and minor axis, and this two coordinate, that is R coordinate, which is basically radial coordinate, and there is the V coordinate, which is basically the angular coordinate. So to make this symmetry possible, this V can have 0 to pi as well as pi to 2 pi. Okay. So based on that, basically two to four sets of solutions will be arrived. And after taking certain approximations and imposing our boundary conditions of ion exchange, we actually reached this final solution over here. And in this final equations, we have actually made the computer programming using the MATLAB, where basically three fundamental modules programming has been developed with respect to different sets of equations. This eigenfunction C2C3 routine actually first calculate the eigenvalues required to generate A and B coefficient, and then after generation of A and B coefficient, we have tried to make a matrix size. We have taken 16 by 16, and we have calculated these two major functions. One is radial, angular, and another is radial function. So angular and radial metric functions once calculated has been plotted, and since it is independent of any system, angular and radial functions are being actually verified with certain other publications whether the functions are okay or not, and their numerical values are also being calculated for different values of that order and different values of uh, q. And ultimately, once we get these two functions individually, we get another program from where we have plotted this resultant function C. And when we plot these functions in two ways, one is angular metric function is being plotted in even or there's a k value, and these k values are being given as a where the q value is maintained same and the order is being checked. So four sets of results of this angular metric function is being plotted, and which is being compared with other results which are showing a good one and matching one. And in the second set of four plots, we have actually made our q value to be valid and this n value remains same. And these values are also being compared. And we have also developed all sets of values, numerical values, which are available in the literature, and we have compared it. So once we make this is the same thing related to the radial function. We also plotted all possibilities and combinations of radial function into ways, and we have compared all these results, and still it is a good one. So based on that, we have actually developed our own concentration function, which is the result of our solutions of this elliptic equation. And we have made different plots with respect to different angular directions of the sample. And here you can see there are functions which is plotted to major axis, this one, and then along 5 by 8, uh, and this is your minor axis, that is maximum 90 degree, and this is in between. This. And we got this result, and from that, this is the basically concentration plot. Normalized concentration has been plotted over here, and from this plot we have developed a iso concentration plot over here and xy plot. So to correlate with our fringe pattern diffusion. So in isoconcentration curve, concentration values are calculated basically from the above routines, where we have taken our sample size 3 by 2 mm square, and thickness is 1.5 mm for 160 hours of ion exchange. And the curves show the elliptic variations of the concentration of the exchanged ion in the glass, and it is observed that the concentration of exchanged ions towards center decreases, and it is expected because when you move inside, the exchange of the ions will be reduced. Basically, there are two processes involved. One is the exchange from surface to the molten salt bath, and exchange ions on the surface go inside by diffusion process. So this diffusion process actually decaying process, and it will be reducing towards the center. So the changes is concentration change will be replicating of this physical process. And it is also to be noted that the along major axis, the exchange of concentration is more than that of along the minor axis. Why? Because along the major axis, what happens? There is a exposed area, and also the vertical uh, the gradient will be higher. So the change of refractive indices taking place more towards this major axis and less towards the minor axis. But the diffusion depth along major axis, which we have achieved ultimately 0.38 mm only, and it is basically corresponding to the sample dimension of 1.5 mm and 3 mm. and focal length. This is fixed. So based on that, you have a maximum achievable distance in certain direction. So beyond this, the result we have not get by this method. So there might be refractive index changes inside the major axis along, higher than this 0.38 millimeter, but we have not measured that part because of the limitations of this measurement calculation. And this observation is basically correlated with this deformed pattern, and you see along the major axis, the changes are more thin changes or deformation, and a minor axis is less, which is correlated with the help of this concentration, iso concentration curve, which is also showing some sort of variations over here. So basically, we did up to this, and we have published this work in LTVR Optics and Communication journal. So in conclusion, we can say that the anamorphic green lens in this system has been developed for sodium and lithium ion exchange process, and the refractive index profile of such unconventional green were measured by reflectometric arrangement with the help of cylindrical birectilinear lens, and the mathematical model for the diffusion process and ion exchange curves involving functions are developed and correlated with the experimental data. And this too is basically the future scope. A thorough quantitative analysis of the refractive index change with the ion exchange change and reanalysis or beam splitting of the developed anamorphic green lens is future scope of study. Though the beam setting and this reanalysis is available in radial green or axial green, but it is not available in case of this elliptical shape of sample. And also this mathematical model can be useful in the mode analysis in hollow core or solid elliptic optical waveguides also. So some sort of elliptical waveguide is being taken out. We use this formulation to develop this new kind of or another kind of applications in case of using hollow core or elliptical core waveguides also. So that's all. And this is basically some publication on this work, and one of the and my this all this work in other geometry also, that is axial geometry and radial geometry. Radial geometry was done by one of our co-authors, and this axial and elliptical geometry work has been done by myself, and all this work has been compiled in a book, Gradient Index Optical Element, Lubrication and Characteristics, and these are the some papers published on this one. Thank you.